Alright, so next we are going to see the notion of relations. And let us now motivate the notion with an example. Let us take two sets. Consider the set of these three letters A, B and C, and another set which consists of these five names: Ali, Bhanu, Binoy, Chandra, and there is another one, Divya. Then we can form the Cartesian product of P and Q. And the Cartesian product, of course, will have all the possible ordered pairs where the first element is coming from P and the second element is a name coming from Q. So we can write P times Q somewhat not that seriously by showing some of its elements. Say with A we will have Ali, with A we will also have Bhanu, and say with B also we will have Bhanu, with C also you will have Bhanu. So you will have all the possible ordered pairs, and you have this also. So by not very seriously, I mean we are not really systematically writing down the elements of this set. We are just showing some of its elements. Okay. However, now consider the following subset R of P times Q. The set R consists of those ordered pairs in P times Q such that X is the first letter of the name Y, because Y has to come from Q. Each Y is one of these names, and each name, of course, being a word, has a first letter. If X is that first letter, then we are considering the corresponding ordered pair X comma Y in this subset R, otherwise not. That means if I write this subset R in roster form, these are the pairs that I will have as elements in R. This pair will be there because for the name Ali, the initial is A, which is this. Not really distinguishing between uppercase and lowercase letters. I mean, it's just A, so A. This, however, this ordered pair won't belong to R because for this name, the initial is B, but the first component is not B. We will, however, have this. We will also have Binoy. And what else is there? We have Chandra, right? and we do have C. And that's just it. For the name Divya, the first letter is D, which however is not present here. So you can see that we have, in fact, described a relation among the between the elements of P and the elements of Q, this specific relation. And we have been able to describe this relation in such a way that it has become a subset of the Cartesian product of P and Q. And this motivates us to define relations in general as subsets of a Cartesian product of two sets. And in fact, what does this relation do? It relates the elements in P with the elements in Q in such a way that the first component, the element of P that is going to be related to some element of Q, is to be the first letter of that element to which it is going to be related. In that sense, this is a relation. So let us now see the general definition. Let A and B be two non-empty sets. Both are non-empty. Although we can consider the cases where say A is empty or B is empty or both are empty, but those cases are not really very interesting because of course, they can be made part of this definition, but because of having empty set, you won't really be relating any element to anything. So in that sense, they are not really very interesting. So in the main definition, we assume both of the sets to be non-empty. Here, in this definition, A and B are going to play the role of P and Q, but they are general, any non-empty sets. A relation R from A to B is a subset of the Cartesian product A times B. That's what it is. Okay. Any subset R of this Cartesian product A times B is said to be a relation from the set A to the set B. Okay. Now let us also write in what sense we are saying that a subset is a relation. Actually, in the text, the definition ends here itself, but I am going to extend this, which is going to include some discussion about these things and also some other definitions that are related to relations. I am going to merge all these definitions into a single one. When R is a relation from A to B and this initial example with which we started, there is something else about this that I haven't said yet. But I will come back to it. Let us first see what this definition has to say fully. When R is a relation from set A to set B, and say this ordered pair belongs to R, we say that X is related to Y by the relation R, or we also say this: X is R related to Y. Okay, so these are some terminology associated with these things. In other words, this set actually gives us the pairs of elements which are related to one another. Okay, so it records all such pairs, and as such, the set R itself defines the relation that we have here. And when you have one ordered pair like this as an element in R, you say that X is related to Y by this relation R. If on the same pair of sets A and B, you have say some other relation S, and there also you have this ordered pair as an element, there however you would say that X is related to Y by the relation S. Maybe that S is some other relation which happen to have this element also as an element in it. Okay, so that's why we mention by the relation R, or more simply X is R related to Y. Sometimes like this also we express this fact. Y is called an image of X under the relation R. Okay, so when this happens, then we say that Y is an image of X under the relation R. Now next, some other things associated with a relation come. The set of all first components of the elements in R. Okay, so this much we have already understood. Any subset of A times B is a relation from A to B. The set of all first components of the elements of R is called the domain of R. Okay, so this is something else, again related to a general relation R. So we are going to understand what this is saying, but let us first write the other things also. The set of all the second components of the elements of R is called the range of R. And besides these two things, the set B is called the codomain of R. Now, it's a little difficult to really understand what these sentences are saying without any example. But still, before going to our example, let us at least see what they are trying to say. The set of all first components of the elements of R is called the domain of R. Now, what are the elements in R? After all, some ordered pairs, right? Maybe not all the ordered pairs in A times B, some of them. Now, each ordered pair has a first component because it's an ordered pair. You collect those first components, take them together, they will form a set. That set is called the domain of R. Similarly, you take all the elements of R, each one is an ordered pair, so each one has a second component. You collect all those second components and they will form a set. That set is the range of R. And this second set B, that set itself is simply called the codomain of R. Now let us go back to that name example, our first example, and see what these things are in that case. So let us first write the set R in our example. It was this, right? A, comma, Ali, B, comma, Bhanu, again B related to Bina, and C related to Chandra. Now, before we try to determine the domain, range and all these things for this relation, let us draw a diagram. This type of diagrams are very helpful in visualizing the relation. Okay, as a drawing, looking at the drawing, you can at once see what is going on, which elements are related to what. So we are going to draw this. Basically is a Venn diagram because we are going to draw two closed regions for the sets P and Q. Okay, so the elements in P were A, B and C. As usual, we draw them as points or dots. And the elements in Q, however, these are the names. Okay, so Ali, Bhanu, Binay, Chandra, and here Divya. Now what we are going to do, we will draw arrows pointing from the set P to the elements of the set Q, so that the arrows have their initial, if for any arrow that we draw here, the place where that arrow is going to start will be one of these points and the arrow will end at one of these points according to this rule. That means there will be an arrow going from A to Ali. And now you understand what else we have to draw. So let me draw the rest of them. Besides drawing these line segments, the way you take these elements, it may happen that some of the arrows intersect each other. So you carefully draw these arrowheads indicating the direction. It's a relation from P to Q. That's why the arrows are pointing towards Q. You draw the arrowheads anywhere on these line segments, but draw them in such a way that they do not get messed up together. Okay. And such a diagram is called an arrow diagram for the relation R. So this above, the above drawing is an arrow diagram of R or for R. It's a visual representation of the relation. Looking at this diagram, you can immediately see what's going on. Of course, you can also see the set R above, but this is another way of expressing the same thing, same information. Alright, so for this relation, we can immediately say one thing, that the codomain is simply Q because codomain is the second set. What about the domain? Domain is the set of the first coordinates of the elements in R. That is A, B, and C. There is no point considering B twice because it's going to be a set after all. So repetition doesn't serve any purpose. Domain is this set, which turns out to be, this is not A, sorry. This is P. P itself in this case, but in general that's not necessary. What about the range? Range consists of the second components of the elements of R. That means range is the set of these names. Note that the range is a subset of Q. Of course, it's always going to be a subset of Q because it consists of some elements of Q, namely those elements that appear as second components or second coordinates in the ordered pairs which are there as elements in R. This name is not in the range of R. Note that range is always a subset of codomain. I am writing these things extremely casually. Okay, you should not use such grammatically wrong sentences. You should write like this: the codomain of R is Q. Okay, if you really want to write, that's how you should write. But I'm not really caring about grammar right now. So, in this one relation, at least we have understood domain, range, codomain. We have also seen that this is how we can pictorially represent a relation as a picture, as a diagram. Now, there are some remarks. These remarks are really, there is no need to say these things. One remark is this: a relation may be represented algebraically either by row-star method or set builder method. Of course, because a relation after all is going to be a set. So you can either use roster method or set builder method to express it as a set. That's one remark. And the other remark is an arrow diagram is a visual representation of a relation. Okay, these remarks sound like they have been written only to fill pages. They do not say anything important. They say trivial things, things that we can already see. But let us next see examples, further examples. Oh, so I can write here itself. Let us see this next example. Let A be the set consisting of the first 6 natural numbers. Let R be the relation from A to A. That means here the two sets are actually the same. B is also A here. There is no need for B to be different from A. You can take both the sets to be the same set. Let R be the relation from A to A given by this. R is the set of ordered pairs in A times A such that y is equal, I should not write the wrong equation. Yeah, y is equal to x plus 1. Okay, so we have to do two things. Depict this relation using an arrow diagram. So that's one thing. And number 2, find the domain, codomain and range of R. So let us first draw the arrow diagram. Even before that, let us first actually write this relation in roster form so that we can see the actual elements. So this relation consists of ordered pairs where the second component should be one more than the first component. But in this type of situations, there is a high chance of making mistakes. Let me show how. Say you start writing the relation. Once you have comfortably understood the fact that y is just one more than x, you become a little careless. You start by having x equal to 1, you write 2 because 2 is 1 plus 1. Then you take x equal to 2, so y should be 3. Fine. This is fun. Next you write 3, 4. Then 4, 5. Then 5, 6. And then if you are not careful, you would write 6, 7. See, the problem here is that the ordered pair should not just be so that y is x plus 1, but x and y both have to be here in A. 7 is not there in A. So you cannot take x equal to 6. It will end here itself. Okay, so this is your relation. Now let's draw the arrow diagram. You can write the sentence, the following is the arrow diagram of the relation. I am not writing those things. Two, 3, 4, 5 and 6. There is no hard and fast rule that you should always write like this. You can also draw a somewhat not so elongated region, and you can scatter the points in that region. Anything you can do. However, if you do such a thing, then the arrows will intersect one another a lot. In order to avoid that, in an attempt to avoid that, we draw like this, usually. But no one can prevent you from just choosing any style. And have you noticed one more thing? While writing the elements here, I have put the names on the left side. Here, however, I have put the names on the right side. That's because I do not want these numbers to come in the way of the arrows. Not here, not there. That's why. So here, both the sets are of course A. And now, here the arrows are also going to look nice. I mean, they are kind of parallel, if that makes any sense. The pattern is nice. In fact, do you see one thing? Instead of writing the relation like this and that mistake that I was talking about right now, here it's impossible to make that mistake. That's because the moment you start taking an arrow from 6, that arrow has no place to land, so that no such arrow exists. Okay, and looking at this arrow diagram, you can instantly see what the domain, range, codomain, all these things are. The domain of R is the set consisting of the places from where these arrows have started. That means 1, 2, 3, 4 and 5. Note that unlike that name and letter example, our first example, where the domain was P itself, here the domain is a proper subset of A. This is the domain. Okay, 6 is not an element in the domain. The range of R, on the other hand, has everything in A except 1. That means 2, 3, 4, 5 and 6. and this also is a proper subset of the codomain, and the codomain is A. So this is the range. And the codomain is A. Don't forget to draw these arrowheads, okay? Otherwise, whoever is going to watch this, they won't know whether it's a relation from which is going this way or that way. Also, do not ever do anything like this. Okay, a relation doesn't usually go both ways like this. By definition, it goes only one way. Don't mix up the directions of the arrows. So that is the second example. After the definition, it's the first example. Next, we have another one. So here an arrow diagram will be given. The following figure shows a relation from P to Q. Let me first draw the arrow diagram and then I will write the rest of the example. P consists of these three numbers 9, 4 and 25, and Q consists of these other numbers 5, 3, 2, 1, 5, 3, 2, 1, and besides that we have -2, -3 and -5, and the arrows that define this relation are going to go like this. Perhaps looking at the numbers you can already guess what I am going to do. 25 is related to -5 and 5. That itself will tell you what this relation is. 4 is going to be related to 2 and -2. And 9 is going to be related to 3 and -3. So these arrows look quite ugly. They have come in the way. So now you can draw the arrows more carefully. Yeah. So what is it that we have to do here? Write it will be nice to already give this relation some name here itself. No? Say I call it R, so that here again you do not have to write let R be the relation. Write R in roster form, or the first one is set builder form. Number 2, write R in roster form. And number 3, find the domain and range of R. So we do not have to draw anything. The drawing is already given. So you can clearly see that I haven't written Q here. The elements of P are related to the elements of Q by this relation in such a manner that an element of P is related to an element of Q if squaring the element of Q gives us that element of P. The squares of minus 3 and 3 are both equal to 9. The squares of minus 5 and minus 5 are both equal to 25. And the squares of minus 2 and 2 are both equal to 4. So accordingly, using this rule, we have to now write the relation in set builder form. In set builder form, R is this. X comma y belonging to P times Q. Oh, if you find it this, although we discussed about it while studying set theory, but if you find writing this a little awkward, writing like this, you can also go for the slightly longer notation. R is the set of all ordered pairs x comma y such that x belongs to P, y belongs to Q, and y square is equal to x. And the second one is easier. In roster form, R is again, there is no set order in which you have to write the elements. You can write in any order, but not inside an ordered pair. Okay, do not write 3 comma 9. That would be wrong. You write 9 comma 3, but you write 9 comma 3 anywhere in this set. Next comes domain and range. Domain, of course, will be the entire set P. Range, however, will not be the entire set Q. the domain of R is P. And if you want, you can write the set, the elements in P. You can show what the elements in P are. Although it's really enough to simply write the domain of R is P. The range of R is this set 5 minus 5, 3 minus 3, 2 minus 2. Yeah, for some reason I can't write this bracket. Okay. Now note that instead of writing this much, you can also just simply write this. From the entire set Q, if you remove 1, then this difference set is nothing but this. So 1 is not an element in the range because it's not being attacked with an arrow by some element from here. And then there is a note. Let A and B be finite sets with the number of elements in A, P, and the number of elements in B, Q. Then we already know that the number of elements in the Cartesian product A times B is just the product of the numbers of elements, that is PQ. Now any relation from A to B is by definition a subset of A times B. So how many relations can we possibly find from A to B? Namely, as many subsets A times B has. In other words, the number of relations from A to B is equal to the number of subsets of A times B. Now we know how many subsets a given set has when it is finite. Since each relation from A to B is a subset of A times B, the number of such relations is the number of subsets, which is 2 to the power the number of elements in A times B, that is PQ. So this little fact tells us exactly how many relations you are going to find from A to B, provided A and B are non-empty finite sets. Non-emptiness, however, we have already assumed in the beginning itself, because of that remark that when one of the sets or both of them are empty, that situation is not really, those situations are not really very interesting. And then there is a small example illustrating this. Let A be the set consisting of 1 and 2 and B has the elements 3 and 4. Then the number of relations from A to B is going to be 2 to the power the number of elements in A times the number of elements in B. That is this. Okay. That means 16. In total, we will have 16 possible relations from A to B. Now, note one thing carefully. This is where actually this section ends. Oh, there is one remark. Yeah, why leave this? If R is a relation from a set A to itself, then R is also called a relation on A. A slightly simpler way of saying this. Instead of saying R is a relation from A to A, because the set is, there is a single set, then we say more simply that R is a relation on A. So this is where the section actually ends. But now I have something to say, something extra. You see, say you have two non-empty sets, A and B. So you can find various relations from A to B. All of them are going to be subsets of the Cartesian product A times B. Among all such subsets, here however I am not assuming that A and B are finite. Okay, A and B may be infinite, one of them may be finite, another infinite, all possibilities are there, but they are non-empty. Now, any subset of A times B is a relation by definition. Among all these relations, there is also this subset. So technically it is also a relation, although a very boring relation. Note that in spite of having A and B non-empty, the empty set of course is a subset of A times B. So this relation is called the empty relation. It doesn't relate any element of A with any element of B, but still, technically speaking, it's a relation. Just like the empty set is a set, the empty relation is also a relation. At the other extreme, you can also have R is equal to A times B itself. This relation relates every element of A with every element of B, because we have all such ordered pairs in A times B. So this relation is as large as you can possibly have a relation in this situation, and this is a relation as small as you can possibly have. This doesn't relate anything with anything, this relates everything with everything. Okay, so these all other relations are in between these two extremes. Now, there are many important types of relations in mathematics. In fact, truly speaking, mathematics is just all about relations only. And let me just name some types. Equivalence relation. It's a special type of relation. Okay, I'm not going to say anything more on this, just the names. order relation. These are not single examples, okay. There are many equivalence relations, there are many ordered relations. These are types of relations which satisfy some extra conditions. And something that we will see in the next section, functions. These are things we won't study right now itself. This, however, we will study. This is also a type of relation. So that means you again have a set A and a set B. And somehow functions are again relating elements of A to elements of B by using some kind of rules. But they are not as general as relations. There are some restrictions which make them functions. These are more important than relations in general. These two are also very important, but this is in fact even much more important than these two. Okay, so in the next section we will see what functions are and in what sense these are after all relations but some special types of relations. So with that, I am ending tonight's video, and tomorrow what do we have? Tomorrow I think we have Galva theory, right? If I am remembering correctly. So that's just it. So see you tomorrow with that. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.